talk about the lab write-up. And let's remember that my memory goes back more than one day,
I'm sure it does.
like yesterday. So you have a complicated lab that you have to do. And when I say complicated, there is quite a bit that has to be done in order for you to produce produce the evaluation I'm looking for, the analysis I'm looking for. And I would strongly encourage you to do the entire thing in a spreadsheet, because most of it is very redundant work. And if you have difficulty, share your spreadsheet with me. I will help you through it. But a lot of it is going to be redundant calculation. There are two things specifically I wanted you to do. I wanted you to measure the moment of inertia of the PVC T, both experimentally and theoretically. So let's go through the theoretical one first, because it's very simple and you should have already done it by now. But I know better. Speaking of, there's a rod about its center and there's a ring about its center. So you needed to take measurements of the length and the mass of just the top portion. And you need to take measurements of the diameter and the mass of the bottom section. The total moment of inertia is just the sum of those two, the moment of inertia of the rod portion plus the moment of inertia of the ring portion. So that's going to be 1/12 mass of the rod times its length squared plus just mass of the ring times the radius squared of the ring. Like I said, you should already have that data. Make sure you convert everything to kilograms, meters, so your values in kilogram, meter squared, because the lab that we're going to do, most of your data is already in newtons and seconds, so that's going to corroborate this. It's not a particularly high number, but it's a reasonable value. So hopefully you took the right measurements for this. If you did not, the apparatus in the back, but you will not be able to probably assemble the same one you had, because all the stuff just gets mixed up. So let's talk about experimentally what you needed to do. Instead of theoretical. You applied a torque. So I'm going to use R to represent the radius of the PVC and F the force from the spring scale. Remember that your lab write-ups will ask you to assign letters to things that might be in your relationships that you might have to then do work on data. So as you assign letters, be clear about what stands for what. That's more an AP1 thing than an AP mechanics thing, but it's still out there. So as you're making up letters for things, be cognizant they're looking for that. When you did this, the torque you applied would be R times F. But the whole time you were doing that, there is a frictional torque that you could not measure directly. Meaning you could not measure the force of friction or the force of air resistance on your device. We couldn't evacuate the room, so we know there's air resistance. In fact, air resistance probably plays as much a role in this as friction does. But there's a lot of friction. It's just rubbing on the top of the ring stand the whole time. This is going to equal the moment of inertia of the rod times alpha A. And I'm going to use alpha A as the speeding up acceleration. Then you immediately stopped pulling on it when the tape came off. And all that was left was the frictional torque, which gave us another acceleration, which I will use alpha s as the slowing down acceleration. We want to be able to factor out or take into account the slowing down acceleration in order to find the moment of inertia. So right away, I hope you realize that's the first substitution we're going to do. The slowing down portion of your lab is to find out what the frictional torque is. I put an R there, but I meant to put an F for frictional torque. So let's study that part first and how we're going to do that data analysis first. To deal with the frictional torque, you have three, I think, pieces of data to which you can look. From your video, you should be able to measure the number of rotations the apparatus makes in coming to rest, probably down to the nearest quarter rotation. The final velocity is 0. That's set. And again, from the video, pretty sure you can measure the time it takes to come to rest. It's just a motion equation here. But I'd be remiss if I didn't write it down, because when I wrote it down in 6th period, several people were like, what? Oh, I guess so. So I'm a little disturbed that I have to at all, but I'd probably use this one, knowing that this is not a term you have to worry about. This suggests that you could set up a spreadsheet to calculate this, because you have a lot of this data. And my expectation is that the frictional torque was probably the same all the time. The normal force on the T-joint was the same all the time. So I would expect the frictional force to be the same. So if I take delta theta, I'd have a column where it's in rotations. And then I'd probably make another column where you convert it to radians. Might as well use the computer for that too. And then you have time. I think you can use that with a formula to come up with your acceleration. If you do this strictly from this function, you'll get a negative answer. But remember, in our force equation, we've taken that negative into account. So I wouldn't worry about it too much right now. Look through this data. Like I said, I would make a spreadsheet and look through this data. Make sure it all looks like it's about the same. If you have any values that appear grossly out of place, then perhaps don't include them in the average. But I would find the average slowdown acceleration. There's another way to do this where you use the specific slowdown acceleration for each calculation of I. If you're good at spreadsheets, I would prefer you do it that way. You're not gonna get extra points or something. I would prefer it. And yeah, every once in a while somebody does it right, and I do grant them more than the value of points that I set for a lab. So people in the room have gotten like 16 or 17 out of 15 on a lab because you've done an excellent job and gone above what I would expect for the minimum student to get an A. Does that make sense? But I'm gonna make it a little easier on you because some of you are not particularly good at it. Sharp students will probably also realize that the faster you spun it, the greater the slowdown acceleration was. Because the faster you spun it, the higher the drag force was on the edges of the wings of that T, and therefore that force was greater, causing a greater torque when it was going faster than when it was going slower. And that will play out as being higher accelerations. It may not work that way because there wasn't that much variance, but it could. Either way, get rid of any values that are probably outside your average. Maybe just drop them to the bottom of your list so you can keep the ones that are good and make those your average and do one calculation of average using your spreadsheet. Yeah. All right, let's go back to this for a minute. You now have an expression for this value that you can get from the first spreadsheet. And if you're using the average, this will be a constant for the second portion of this. If you want to use the individual values, then you're going to have to be a little more careful on your spreadsheet. And I'll show you what I mean by that. Because we're going to do this substitution. And we'll get RF minus I alpha S average equals I alpha A. Now, we want I. So you can either use the y equals mx plus b version to find the slope, and then from there get the value for I, or you can do the solve for the unknown version. Both of them will fit this if you know how to apply it. I'm going to do this version of linearization, but either version of linearization will work. So to do this, I'm going to solve for I, which gives us RF equals I alpha A plus I alpha S average. Factor out the I. And solve for I. Because we have something that's measurable both on the top of this fraction and the bottom of this fraction, this is why we could use the solve for it version to get to I. Plot this on the y-axis and this on the x-axis, and it should produce a graph whose slope will give you k. I'm sorry, give you I. Okay. Now, speaking to what you asked, you have to solve for alpha A here, and you're using slightly different data. So you have delta theta while it's speeding up. This is probably a constant if you did this the way I demonstrated. You wrapped it the same number of times every time for the pulling portion. So that's probably a constant. It started from rest, and you timed it. This is the only thing that you measured. So a spreadsheet could have t in it, a calculation for the acceleration that comes from delta theta equals 1/2 alpha t squared. And then if you're looking to use a spreadsheet for this, you could have your next column just be alpha A plus alpha S average to get this column. Or use your other spreadsheet and don't use the average, use the slowdown that you got for the speed up that you're measuring, right? Because you have the slowdown and speed up on the same measurement, on the same video. So you could just use this spreadsheet over there and be adding this column to this column to get this. Does that make sense? Yeah. That would be better, because then you have the slowdown matched with the speed up. This would account for the difference in the accelerations due to air resistance, and would do a better job filtering it out. You're welcome. And then another column where you just compute RF. Remember, this needs to be in radians. This needs to be in seconds. This F is already in newtons if you use the right spring scale, but R needs to be in meters. All right. You should show me in your lab that the units of I work out from this to kilograms meter squared. And you should further show me how this value for I relates with this value for I. Does that make sense? All right. What I want to see in your lab, I want a standard lab write-up, starting with the purpose of this lab is to measure the moment of inertia of the PVC-T. I should see this discussion about why the measurements you took are able to lead to a way for finding I. I should also see a small discussion about how you could theoretically determine the value of I. I don't need you to prove using calculus or anything, just use the accepted values and say how you're theoretically showing it. In your analysis, I ultimately want to see how you did your calculations. So if you use a spreadsheet, that's fine. Just include the spreadsheet data in your lab write-up. Eventually, I do want to see this graph with your data set and how you found the slope of that graph. And then a sentence or two where you compare this value to the value you got theoretically. You can do all this by hand, but I think a spreadsheet works better. If you're gonna do it by hand, have fun. I think a spreadsheet does this in about 2 to 3 minutes per sheet. I think doing it by hand is gonna take 20, 30 minutes per set of data. So use your time efficiently. That's why I taught you how to use a spreadsheet. But also, I want one PDF document, and I don't want that PDF document to be a collection of pictures of your computer screen, which is what you guys turn in. I don't like that. I don't mean it's mean, but do better. Use the tools to your advantage. If you don't know how to import something from Excel into Microsoft Word, ask me, I will show you. Or do the whole thing in Google Docs, because it does make some of that stuff easier. But that's on you. Eventually, I just want a PDF. Some of you in your last lab, which had to mix pictures and stuff from Excel, just turned in the Excel file. I gave you half credit. I don't want that. You are telling me a story. I want to read the story. Everybody understand? All right. I could show you exemplars. I have some from this class that are what I'd rather see, but I don't want to embarrass those students. If you need an exemplar, I'll provide one.